So everyone, thank you so much, first of all, Kulbir, for the invitation here. And lovely to meet some of you for the first time that I've been speaking with, I guess, for the last few years now. Wait.
Thank you, John. No,
no worries, it's fine, it's fine.
I'm very small. But sorry. Yeah, there we go.
Very good. Okay. Yeah, so it's really a pleasure to be out here. I had a chance to chat with some people yesterday, and I was getting a little bit out of my depth before coming here, and I'm getting even more out of my depth now. I'll explain why in a moment. So the talk today is going to be an extremely sort of speculative talk. There's not going to be a great deal of detail. One question that I have actually for everybody here, just in terms of people's background. So who here, as an example, has a general intuitive understanding of how a neural network works? Okay, about half, I would say. Okay, and how a transformer works? Okay, no, that's perfect. That's kind of what I was looking for. So I want to talk about just some speculative ideas about how we might use some of the ideas from transformers, other models as well, to think about the sort of rich embedding spaces that they produce and how we can use those to think about models that actually understand, and I'm going to use that word a number of times, understand physics so that we can use them for the sort of material design that many of you will be talking about here. So just a little bit of my own background. This is my sort of the shop lab tree here, some of my students, and this is really, you probably can't see the details here, but I work in a fairly diverse range of areas, and I'm certainly not a material scientist. Most of my work at the moment is actually in reinforcement learning and active inference. I'm very happy to talk with people about that. I won't be talking about that today. Incidentally, this picture was created by one of my ex-students, Caitlin Sparks. This is not my own design, but she did yeah, so then we'll get into the details. So I'm going to be talking sort of as if I were a computer scientist today. I'm really a physicist. I did my PhD in theoretical physics, but over the last 10 years or so, I've sort of moved more and more into machine learning, into data science. A lot of the work has been on neuroscience, neuroimaging, and now working with Kulbir and team on the sort of material science side. So I'm not a computer scientist. I'm also not a material scientist, so I'm not entirely sure why I'm here. But I think I'm going to have something to tell you. Yeah, so the talk is going to be fairly vague and somewhat speculative. And this has really been working with Yasser, wherever is he around, who will be back, our joint PhD student. And just some ideas that I've been thinking about over the last couple of months, and really just throwing ideas out there. It's very likely that I've missed some pretty important parts of the literature. So if you can tell me that everything that I'm going to talk about is either wrong or has been done, then that's going to save us a lot of time. Okay. So I actually want to start off with a sort of misunderstanding. And what I say here is the conversations between people in machine learning and other scientists can be frustrating. And I'm looking at you, Kulbir, but I'm saying this because I was actually wrong. Okay? So we had discussions some time back about what machine learning could do for material science. And I think there's often this case that somebody from other areas of science sort of sees that if you throw some bits of data, the machine is magically going to learn physics and will be able to make wonderful predictions. And this is a difficult conversation between somebody not in machine learning and somebody who is sort of in machine learning. And actually, in a sense, I've come to sort of change my mind a little bit. I think that while, just with a few bits of data, it's very difficult for a machine to really learn the underlying structures. I think that actually there is some idea that machines can sort of understand in what we're seeing in these complex embedding spaces, in particular, the sort of transformer embedding spaces. Is this okay? This is sort of ironic. I took this slide and I passed this into ChatGPT, and I wanted to have some sort of image to put up here of what would illustrate this, and it gave me instead what it would look like if you were all sat here, a photo behind, and I just translated all of the text into some W. Okay. So the general plan for this talk, I want to talk about the bitter lesson. I don't know how many people here know about the bitter lesson, Rich Sutton's bitter lesson. Okay, we have one, good. I want to talk a little bit about the workings of a neural network, and this is going to be a real sort of a fairly hand-wavy overview. It's good. So, okay. Good. Okay. And then talk about embedding spaces in transformers, and in a sense, how we can use some of these ideas to think about material design, understanding material properties from thinking about the sorts of embedding spaces which emerge from training transformers, things like GPT on text. I talked about some projects that other people are doing, looking at neural networks, actually learning physics. And this idea of understanding and learning, we tend to anthropomorphize a bit, but I think it's actually a really important and interesting question, what these sort of models are actually learning. I'll then talk about multitask learning, which I think can give rise to these very rich embedding spaces. And then ask the question, what can these models actually understand? What's going on? What are they really learning? Are there any parallels between what they're learning and what we understand when we think about the science, the physics behind materials, for instance? And then just at the end, sort of a vague notion of what a model might look like that can do material science, the types of questions that we're asking about material design, for instance. So there's lots of text on here, don't worry about this. So this is an essay from 2019 by Rich Sutton. Rich Sutton is one of the people who was really influential in reinforcement learning and developing reinforcement learning. And of course, Sutton and Bartow wrote sort of a canonical textbook on reinforcement learning. But in 2019, he put up this essay, and it's called The Bitter Lesson. And just reading out some bits of it, the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margin. Seeking an improvement that makes a difference in the shorter term, researchers seek to leverage their human knowledge of the domain, but the only thing that matters in the long run is leveraging of computation. The human knowledge approach tends to complicate methods in ways that make them less suited to taking advantage of general methods leveraging computation. And the lesson here, what he's really saying is that the idea of sort of creating handcrafted features, sort of manipulating data sets into ways that we think are going to be useful for the computer to understand, in the end are sort of beaten by simply using bigger models, larger compute. Okay? So the idea is that yes, in the short term, maybe you may be able to get gains by doing intelligent feature engineering. But actually, if you just throw more compute at it, the bitter lesson is that at the end of the day, that seems to work. And this is a bitter lesson because, of course, the domain expertise that everybody coming to these fields has. While clearly, it's important in the short term, the question is, can these models learn without our having to step in and tell them, in the same way that in the first instances of artificial intelligence, it was really about engineering the features, hand coding the algorithms, and this is saying more compute, bigger models. And we don't know, for instance, for large language models, whether this is going to be the case forever. There's going to be some plateau in what they can do, but we're finding that the emergent properties of these models are incredibly powerful and continue to surprise us. So I apologize to those who do work in machine learning. This is going to be an extremely sort of hand-wavy idea. But so what's actually happening with a neural network? I'm just going to take a very simple example where we have some data sets. I've just made up this data, and this is non-linearly separable data. So we have two classes. One is red and one is blue, and there are just two features here, the x and the y directions. These are two features. And by non-linearly separable, all we mean is that there is no straight line that I can put through here that separates one of the classes from the other class. Simple as that. And so the question then is, how can you use a machine learning model to find some separating surface within a data set like this? And this is really sort of heuristic way of thinking about it. But here we have two features, we can call them X and Y, and we can pass it into some fairly simple neural network, add in some nonlinearities, and we can go up to some three-dimensional space, from a two-dimensional space here to a three-dimensional space. And within that three-dimensional space, once the network has learned on this data, this isn't going to happen if you just have random weights and biases here, but once it's learned on the data, it learns to create this three-dimensional feature space, this latent representation, where now it's clear that I can have some linear separation. There's a plane here which can nicely separate one class of the data from the other class of the data. Now, what's really happening here is that we're simply doing linear transformations and then adding some nonlinearities here. Again, this is very hand-wavy, but this is the general idea. That's all you're doing with a model like this, is linear transformations here from a two-dimensional space to a three-dimensional space with some generally very simple nonlinearities added in, such that we can find some representation of this data where we can nicely separate the two classes. And indeed, you could go down to another two-dimensional representation. So now we have the representation in 3 dimensions, but you can now project it here onto, I guess, the ZX plane. And now we're back to a two-dimensional representation, where in this two-dimensional representation, there is a straight line which separates the data. Okay? So that's the general idea. And even though what I've drawn here is a very, very simple model, in fact, what's happening in even sort of the complex transformer models, that sort of thing, it's really very similar. It's really just some linear algebra. The learning is happening by backpropagation, just gradient descent. And maybe there are some nonlinearities thrown in there, but that's really all that's going on. So the important point here is that the network is learning some good representation in some slightly different embedding space where the data is now nicely separate. So I've actually taken this from a really nice video from 3 Blue 1 Brown, which I think is the most intuitive explanation of transformers that I've come across. So what's a transformer doing? And I'm talking about a transformer here from the point of view of sort of large language models, sequence modeling. So here, essentially, all you're doing is you're taking the words in a sentence. So this is the sort of technology behind ChatGPT. You take the words in a sentence. Words, they can be parts of words. Each one of those words is transformed into a vector in some relatively high dimensional embedding space. So over here sits the word A, over here sits the word fluffy, over here sits the word blue. So each of these here is just some vector in some moderately high, a few thousand dimensional vector space. Okay? And in fact, those embeddings themselves are learned. So with the training, you learn precisely where within this space these words live. The point is that then you're just doing, again, some learned linear transformations on your data. And the way this really works is that what's happening is that the last vector, the last embedding vector in your sentence gets updated by all of the previous ones. Okay, and I'm going to show you that in a moment, precisely how that works. But for instance, the word blue here, the word before it is fluffy. And so some point here, blue, is going to be updated with everything before it. Okay? So there's some relationship, and essentially it comes down to one embedding vector asking questions of other embedding vectors and saying, where should I move to? Okay? So in this case, we've got fluffy blue creature. So over here is fluffy, over here is blue, and over here is creature. And those correspond to very, very simple concepts in this embedding space. But what's happening is as you pass this through the attention layers, is essentially that last vector, for instance, the one corresponding to creature, gets updated to a more complex, richer representation that corresponds not to the word creature, but to the idea of a fluffy blue creature. Okay? That's really what's happening. And then at the end, once everything has been passed through multiple of these multi-headed attention layers, what happens is you end up with a single vector that essentially encapsulates the entire concept of the set of words, the paragraph, or of course it might be some multimodal data, but essentially you just have a single vector in some high dimensional space that encapsulates all of the information in the sentence. Okay? And essentially a transformer through the training is learning about this high dimensional space. Over here sit certain types of concepts and over here sit other types of concepts. And we're only beginning at the moment to understand precisely how these spaces work and learning to sort of read these spaces. In fact, there was a recent paper actually from the University of Toronto that came out called What's the Magic Word? A Control Theory of LLM Prompting. And this is a really fascinating paper that essentially says, what sort of control do we have over this, this embedding space, this very rich embedding space of concepts? And although large language models are, of course, trained on language, they seem to be learning something about sort of the relationships between ideas in the real world. There are these famous examples that there are sort of analog directions. So here, there's a male-female direction. So if you look, where is the point in space where the word man sits and the place where woman sits, and also the relationship between the point where the word king and queen sits, the relationship between them, the direction is the same. There is some direction here that tells you about the sort of male-female direction. Or verb tenses, the point in the space where it says, which is corresponds to the token walking and walked, and swimming and swam, those are sort of related by pointing in exactly the same direction. And so the learning of the embedding space itself, which just happens through training on, around, what is it, a few hundred gigabytes of text data, which doesn't sound like a huge amount because it's on a computer, but actually most of the text data we have access to, seems to learn the relationships between these concepts. Okay? And this paper starts to look at how we can actually understand moving around within the space and how we can control the other. Of course, this is a big question with sort of AI safety. I also just wanted to point out this rather beautiful book, Fluid Concepts and Creative Analogies, written by Douglas Hofstadter, the author of Gödel, Escher, Bach. And essentially, he's talking about analog as at the heart of intelligence, understanding the relationships between things as being very important for our own understanding of how the world around us works. In a sense, we sort of think in analogs, and it may be an analog to past sentences that you've heard. If I ask you to pass the salt, and you've never heard anybody say pass the salt, but you have heard somebody say pass the water, okay? You just draw an analogy there. There's some relationship between those sentences. And because you understand another analogy, you can learn through having that understanding of the structure of this concept space. So what's the transformer doing? Well, it's sort of iterating on meaning. And again, this is really simplified and slightly misleading picture, but this is the general idea. So here we have a sentence, the big happy mole. And in fact, the word mole there is quite important because, of course, for chemists here, the word mole has a very different meaning to a zoologist, or to a dermatologist, or to a spy, for instance. So all of these people will hear the word mole and they will understand it as something very different. So what the transformer is doing, what the technology behind ChatGPT is, it's updating. So mole just sits at some position in this high dimensional embedding space. And via the words around it in the text, it gets moved to a position in the space, which is actually the one which is salient to the particular sentence. So the big happy mole, well, this probably corresponds to the sort of zoological meaning of the word mole. And each of these points here corresponds to one of these words, big and happy and mole. And the word mole gets moved to a new point where this point in the space corresponds to the idea of happy mole. And then it gets moved to another point which corresponds to the more complex idea of a big happy mole. Okay. Now, why on earth am I talking about all of this? So what's this got to do with material science? So with transformers, what we're doing is we're taking a sentence, and the transformer through training is learning to embed it. Okay. So you start with data in general in a very raw form. So you don't want to manipulate the data. You don't want to do too much hard coding, too much feature engineering. There is actually some very interesting science behind tokenization i.e. how do you take the particular parts of words and tokenize them before you turn them into embeddings. But the point is that you really want to take this data in a fairly raw form, not do too much with it. And the transformer learns about this embedding. It learns about what are the things that are sort of similar and what are the analogies within this space. The transformer then sort of looks at the relationship between these, and we can draw out of this within the embedding space. We can draw out these analogies between ideas. And in particular, when we're utilizing the neural network, the transformer at inference time, when we're actually running it on some new data, what it's doing is, as I said, it's taking all of the pieces of information and combining them into a single point in this high-dimensional embedding space that corresponds to this very complex concept. And the last layers of the network tend to be relatively simple. You've got this point now, it's encapsulated everything about your data, the entire sentence, and you can then take this, and if you're doing next word prediction, then you may just pass this through some multi-layer perceptron, a very simple neural network, and it just gives you a probability distribution over the next likely words. So why might we be interested in this? Well, coming from a very naive point of view, I think about sort of molecular structures as having these, points in some embedding space, and there's relationships between the atoms within these molecular structures, and I can think about single points in embedding space that are updated from a crystal, from some complex structure. That what I'm interested in is the relationships between atoms. Okay, this is just one particular example. I'm interested in the relationships between atoms. One atom, if I take a single point as a single atom in some crystal, for instance, I put it as a single point in the embedding space, and here's another atom, and here's another atom, and here's another atom. What I'm interested in is the relationships between them, so that I can pass this through some multi-headed attention. And by multi-headed attention, I essentially mean each atom is asking questions of all the atoms around, okay, such that I end up with a single point which corresponds to the entire crystal structure. And then I can ask questions about the crystal structure. For instance, what are the properties of it, or where might it move within the embedding space if I heat it up, if I perform particular physical manipulations of it? Where is it actually going to move within that space? Because a transformer naturally understands about relationships between words or any sort of token. So for large language models, of course, it's about the training data. It's not about us saying to it any more than just passing in the training data. What are the relationships between words? We don't have to say, okay, well, over here, these are animals, and over here, these are plants, and over here, these are emotions. It learns all of this naturally from the data, and you need a lot of it. And the question I'm asking here is, can one do something similar for material properties, or even think bigger than this? So this isn't a unique idea. There are various papers that have looked at transformers for material design and for understanding material properties. So Atom GPT, atomistic generative pre-trained transformers for inverse material design. So these sorts of ideas are already out there. Discovery of 2D materials using transformer network-based generative design. These tend to be relatively specific for two-dimensional materials. This is a particular benchmark study of these sorts of material transformers. And so this work is out here. And looking at the sort of work that people are doing, it tends to be the case that people are looking at fairly specific questions, a particular class of materials, for instance, or looking at particular properties. And I'll come on to why that's important in a moment. There are many interesting non-transformer-based approaches. So, in fact, Alex here, I think, is going to talk about crystal GFN, I believe tomorrow. Google have also looked at various graph neural network models. And essentially, this is about material exploration. So how do you move around within the space of materials in order to come up with ones of the billions of potential ones, come up with ones which are likely to have the properties that you want, so that you can utilize the fact that these models tend to be very fast at inference time, They may be slow to train, may take a lot of energy to train, but at inference time, they tend to be very, very cheap. There's another paper here, which I think is a very interesting one as I was researching this. This is really looking at various different approaches to understanding electronic structure learning of electronic structures using machine learning. So the question I have here is, can a model really learn physics? In the same way as a transformer seems to be learning something and actually understanding the relationships between things. What does it mean for a model to learn physics? And the question here, I think, is also about how sort of wide your vision is. Do you want something which is going to learn about a particular class of crystal structures or crystal structures only? Do you want to have something which is learning about both classical and physics? So just quickly, there's actually a project out here already called Polymathic, the Polymathic project. And essentially, this is a project which is using transformer architectures to learn physics. Okay? And it's learning physics by training on many different types of data. And actually, what you're seeing here, these are fluid dynamic simulations, the ones down here, the truth being that comes out of the simulation. And at the top is the predictions from a neural network, which has learned on lots of simulations, okay? And seems to do a very, very good job for a fairly large number of steps of inference to make predictions about fluid dynamics. And the question here, I think, is, is it understanding fluid dynamics, or is it just running its own internal simulation? And a question that I have that I think is important to think about is, what does it mean for us to understand something? Is it just about that we're able to perform these simulations? Is it just that we can translate it into another language, into the language of mathematics rather than the language of computer simulations? But these things seem to be sort of learning underlying structures, underlying physical principles. Nice paper about rediscovering orbital mechanics with machine learning, and this was actually using graph neural networks. And essentially, you pass in training data in the form of trajectories, and it's not just that it's able to make predictions, it's actually able to build a model, a physical model of the relationships between bodies that actually tells you about the orbital mechanics equations that we already know. So these systems can learn the underlying physics from the data. I think the other important thing is about multitask learning, that you learn about particular properties of materials, not by studying that material in and of itself. That wouldn't be enough for you to understand it. You learn many different things, asking different questions, and through that multitask learning, you're able to build up in yourselves very rich understandings of physical properties, of chemistry or physics or whatever it may be. Multitask learning, certainly in large language models, seems to be very powerful as well. So the T5 architecture, which is a different architecture from ChatGPT, works by giving it many different types of tasks, from sentiment analysis to next word prediction to question answering in terms of facts. And you pass in some tag which corresponds to the task that you're training on at any particular time. And the point is that the embedding space seems to be very rich. So by doing learning on many different types of tasks, these models can learn these very, very rich embedding spaces. So this very naive call in for a sort of foundation model that's able to learn a fairly broad range of different problem approaches. It is really to say, what can a transformer learn about the types of problems that I know many of you will be talking about over the coming days? And can one actually have some sort of foundation model that uses something akin to federated learning, where essentially learning is decentralized? Everybody here has these interesting data sets, but they may be relatively specific data sets. Can one have a transformer model which is able to perform multitask learning? Each of you may be looking at some different type of problem, but you perform multitask learning on this foundation model, which is able to understand something about the physical properties of the types of questions that we have here. I think my time is probably up, so I will stop there. Thank you very much.
Thank you.
Thank you very much for this very inspiring talk. Do you think you talked about visual structures, and the properties of visual structures are mainly controlled by the electron density distribution. Do you think that we can describe this using transformers?
Yes, so I think again, a part of it is about the representation that you have passing it in, and I think very naively the question is what is the sort of least manipulative representation you can have? What is the purest representation? In the same way that you don't fiddle around with the words in a transformer, and so the question there, not as a material scientist, is asking you the question: what's the rawest form that you could put it into? Rather than trying to put it into some encoding, can you simply take that density and put it in a raw form? And if so, is that the right thing to do? I don't know the answer, but I think that's the question.
You can take one more question.
Go ahead.
Okay, thank you for the presentation. It was very interesting. You mentioned in your discussion of the mountain project that most of the question to understand how these models understand physical concepts. So if I'm not mistaken, transformers adapt almost quadratically comparison to sequence line. So they're quite computationally costly. So how would you ensure, or how do you think we would go about ensuring the robustness and resilience of these models?
Yeah, so there are various other models like the new state space models, things like Number, which seem to have better better computational complexity. So I'm not necessarily saying the transformers are the right model to look at here. And yeah, absolutely, the sort of computational complexity is clearly an important problem. I don't know, if you're looking at multitask data here and the types of the size of the data sets that people are looking at, what sort of compute one would need. That's an important question that I don't know. And whether the fact that it may be sort of quadratic in terms of the complexity, whether that's a problem or whether actually the scaling, there's sufficient compute given the size of the data sets that people have. So it's a good question. I don't know the answer.
All right, thank you, Jonathan. Let's take our